Okay, we're gonna start talking about some different stuff. I'm really excited to get. You find them? Put that away.
It's like photoshopped.
I don't think it's photoshopped, Alex. You're wrong.
What's that?
Neil.
Neil.
Okay.
Yes. All right, so let's have a look. So we're looking at some new stuff here, lines and angles. Different stuff. I'm excited to get going. I feel like we've kind of laid the foundation now. We've done all the necessary stuff to be able to kind of move through material a little quicker. We've reviewed algebra. We've practiced kind of using the idea or the model of taking geometry concepts, turning them into algebra equations. So you've had some experience with that. We've looked at some proofs. We've looked at how to construct proofs, and so we're good to go. We can just start looking at new geometry concepts and applying those ideas to what we're studying. So lines and angles. All right. So we want to be able to look at, what do we want to be able to do here? We're going to talk about relationships between lines, and then we want to talk about some relationships between angles that are formed by lines. This is going to be, I think, largely review for a lot of you. It wouldn't have been in the past, but I think you've covered this stuff, which I'm glad. You've covered this stuff already a little bit in middle school, so it'll be, this will be probably a little bit of review. So definitions of some different kinds of lines. We all know what parallel lines are, right? Okay, parallel lines are lines that, what? What do they do?
They never intersect.
Okay, they never intersect. Okay, do they ever get any further apart?
No.
Okay, good. That's the definition you've been taught, and we'll stick with that, although it's not technically always true. And we'll talk about why that is maybe later. But there are situations in the universe where parallel lines do in fact cross, and there are places in the universe where parallel lines do in fact diverge. We'll talk about that later, but that's true. But if we're going to presume that we're in a normal space, in what we call a Euclidean or a flat space, and for our geometry, think about the kinds of geometry that we're doing right now. We're doing the kinds of geometry that we can represent on a flat board, right? And so on a flat board, parallel lines do always stay the same distance apart, never intersect, never approach each other, never diverge, right? We'll talk some more later. I mean, I'm not gonna do it today, but you'll like this. A good conversation, interesting. We'll talk about how that's not always true though. Skew lines. Skew lines are lines that never intersect, but are not parallel. Okay? And then parallel planes. And we even mentioned this before, parallel planes. What are parallel planes? Give me an example in the room of parallel planes. Okay, good. Ceiling and floor, left and right wall, front and back wall, etc. Right? So those are pieces of planes that are parallel, planes that never intersect, right? Okay, they're always the same distance apart. Okay, so on this diagram up here then, I would like you to name for me somebody, and I'll call on people here. Let's be thinking about this on your own though. I want you to name a line that is parallel to line AB and contains point D. Parallel to AB and contains point D. Duncan, what do you think?
Easy.
Well, how would you say it though?
Line segment DC.
Or line DC, right? Yeah, does that make sense? So line DC would be parallel and it contains D. Why is it, oh, well, never mind. Everybody sees that. Any questions on that? Okay. How about a line that is perpendicular to AB that also contains point D? What do you think? Cassie? Line that's perpendicular to AB and contains point D. What do you think? Suggestion? Matthew, you have an idea?
Would it be angle DH?
No, I don't want an angle. I want a line.
I mean line DH?
DH. Is that
No,
perpendicular?
would it be AD angle, or line AD?
Yeah, line AD. You see that? If I draw that in, would you agree if I draw a line AD, those two are gonna meet at a right angle, aren't they?
Yeah.
Okay, they sit in the same plane, right? Okay, can somebody name another line that's perpendicular to line AB? I don't care what point it goes through. What do you think, Kurt? Say it again? BC does too. Name another one, somebody.
Line HA.
Line HA, oh, I didn't know if anyone was gonna pick that one. Yeah, that's a tricky one. Everybody see, that was a hard to draw, but if I do line AH, would you agree that those two actually do meet at a right angle? Right, if I extend this out a little further, they meet at a right angle too, don't they?
Line BG.
Which one?
BG.
BG would work too, yeah.
AG. AE also work.
AE would also work. Yep, there's lots of them. Okay.
I don't think it goes to QA.
QA, no, I don't think that was gonna work.
Where's here?
Okay, what about this one? I want a line that is skew to line AB and contains point D. Elimination, can you name one that's skew to AB containing point D? Line DH works, doesn't it? Right? DH works because we can see that DH does not intersect AB, but it's not parallel, so therefore it's gotta be skewed. Okay, what's another one, Daphne?
Line DG.
Say it again?
Line DG.
Line DG, yeah, it's a tricky one. Line DG works, doesn't it? If we do line DG, that also misses this line, but it's not parallel. Yep. EF work, which one? DF. Yeah, DF works. So that's even a harder one to draw. So that one starts there and it kind of goes back through there, right? And then it pops out right there. Let's go through those 2 points. That works though. Okay, we got the idea, right? Okay. And there were more. We didn't get them all. There were more. Okay, now how about this one? Name the plane or planes that contain point D and appear to be parallel to plane ABE. How many points does it take to define a plane? 3. And there's something a little more than that. It takes 3 points, and the 3 points have to be. Say it again. Well, they have to be a right angle, but they have to be, well, coplanar. Right, but they have to be, what else? Like, for example, what if I put a point right there? Oops. What if I put a point right here? And I call that,
Oh, yeah.
say it again?
Can we call it?
They have to be non-collinear, right? They can't be, if I want to define a unique plane, I have to have 3 non-collinear points. Like if I were to pick a point, if I called this point J, for example, points A, B, and J, those are all on a line, and so how many planes would be defined by those 3 points? Well, okay, on this drawing, there would be maybe 2 of them that are obvious, right? The top face and the side face.
Oh, and then
But then I could also do a diagonal one maybe, right, that goes from this edge up through that edge. How many are there total if we just disregard the infinite number, right? I mean, infinite number of planes that we could have intersect that line. So that's not enough, right? It can't just be 3 points, it's gotta be 3 non-collinear points. So if we do the points A, B, and E, how many planes go through those 3 points? 1. It would be the left face of the cube, right? So name a plane that contains D and is parallel to that then. What do you think?
DCG.
Luke, what do you got? What's
DCG.
DCG? I could do plane DCG, couldn't I? I could name it differently. I could pick a different 3 points. Could I come up with a different plane? I can't on that cube, can I? Are there other planes that are parallel to ABE? Sure. I could have one over here that's turned it right, that's parallel to both of them. But there aren't any other planes that I could define using anything other than those 4 points, right? Because that's on the cube, that's the only other face that's parallel to the left face, right? Make sense? Okay. Okay, so a couple things here. We got some postulates. I added some, and I haven't printed it out yet. Actually, I probably will print it out today and give it to you. But I'll add it to Moodle also. I've added the chapter 4 proof reasons, and here's one of them. This is a really big one in geometry, the parallel postulate. We get a lot of mileage out of this in geometry. Makes sense. If there is a line and a point not on the line, so say we've got line L, the blue line, and we've got some point P that's not on the line, then would you agree, doesn't this make sense? And it's a postulate. And remember, postulates are things that we don't prove, we just accept because they're so obvious. Does it make sense that there's exactly one line through the point parallel to the given line, parallel to L? Right? Does that make sense to you? There's no way you could possibly come up with another line through point P that would be different than this one and still parallel to the blue line, right? Agreed? If I keep it in the plane, it's got a tilt, and therefore it's not parallel. If I take a line out of the plane, then it's got to be skew, doesn't it? Right? What do you know about all parallel lines? How many, if I take a pair of parallel lines, how many planes are defined by both those lines at once? One, right? Does that make sense? If I have 2 parallel lines, then those parallel lines sit in only one plane simultaneously, right? For train tracks, it would be the plane of the flat ground, okay? So that's the parallel postulate. Going along with that is the perpendicular postulate. Same kind of an idea. If we have a line L, the blue line, and a point P not on the line, then there also is exactly one line through the point that's perpendicular to the given line, right? And once again, they reside in a single plane, the plane of the board in this case, right? Okay, some definitions. Did you talk about transversals and lines last year?
I don't remember.
Okay, so raise your hand if you remember talking about transversals and angle relationships. Was it 7th grade? Maybe 7th grade? Okay, so it's been a little while ago, so we probably want to review. So some definitions. A transversal. Now you got to be careful with this. Transversal is a line that intersects 2 or more coplanar lines at different points. Okay, so the lines have to all be coplanar. And it would look something like this. Is this an example of a transversal? So what if I drew is the red line a transversal?
Yes.
Yeah, it is. Okay. Is the purple line a transversal?
Yes. Yes.
See if it fits the definition. Does it intersect 2 or more coplanar lines at different points?
Yes.
It does. At the 2 purple points, right? It intersects 2 different green lines at 2 different points. So it's a transversal, agreed? Okay, what about the orange line?
No.
Well, that crosses 2 lines, right? So why is it not a transversal? Okay, it crosses at a single point, so that doesn't count. So that one is not a transversal. Okay, all the other ones were though. Okay. So now, if we have a situation like that, where we have 2 lines that are cut by a transversal, then that creates a situation where we've got a bunch of angles, right? In fact, we get 8 angles. Every time 2 lines intersect, they create 4 angles, right? So 2 lines being intersected by a transversal creates 8. we can discuss those as being in relationships, right? We can say that angles 1 and 5 are what we call corresponding angles. Because here's how, I mean, what's a way to think about those as being corresponding angles? Anybody want to give us an idea or a model we could use to remember that? Any ideas? Why are 1 and 5 corresponding? What do you think?
Because they're in the same position in relationship to the transversal and the other line.
Okay, good. They are in the same positions relative to the transversal, right? So in this case, they're all in the upper left. Another way to think about that would be, what if I took the bottom line and I just kind of moved it and dragged it up so it covered up the top line? What would happen to angles 1 and 5?
They'd be the same.
They'd overlap, wouldn't they? Okay, so therefore they are corresponding angles, right? Okay, what about the other ones? We'd say that angles 1 and 8 are alternate exterior angles. Angles 3 and 5 are, whoops, that's wrong. Oh, 3 and 5 shows up twice. So it should be probably 3 and not 5, but what should it be? 3 and 6, you're right. It should be 3 and 6 are alternate interior angles, and 3 and 5 are what we call consecutive interior angles. Okay, so what does that mean? What do you suppose alternate means in that case? If I talk about alternate angles,
They're on the different sides of the transversal.
okay, they're on opposite sides of the transversal. Okay, so 1 and 8, for example, are alternate angles because 1 is on the left of the transversal and 8 is on the right. What about 1 and 8? Why are they exterior angles? Okay, good, because they're on the outsides of the two lines, right? So therefore, if I wanted to describe 2 and 8, for example, how could I describe 2 and 8? Okay, consecutive exterior. So what does the consecutive mean then, as opposed to alternate? Same side of the transversal. Okay, so consecutive versus alternate. And then exterior or outside, 4 and 6 I would describe as what then?
Consecutive.
Okay, consecutive because they're on the same side, and interior, so what does interior mean? Yeah, between the two lines, okay? So interior is between, so then 4 and 5 I would describe as what? Alternate interior. 2 and 7 would be alternate exterior. 3 and 5 would be, okay, consecutive interior. 1 and 7 would be consecutive exterior. Consecutive exteriors always get left out for some reason, but we want to give them a break. So you're going to help them out today in just a second here. You're going to show that they can be valuable too. We're not quite there yet. So that's it. Okay, so that one's really short. Okay, but now what I want to do is so that all we did there really, what was that all about? All we did was some definitions. We defined what skew lines were, what parallel lines were, what parallel planes were, and we defined a transversal. And all we did was we said that the 8 angles that are created when 2 lines are cut by a transversal can be related as pairs. Okay, now what can we do with that though? Well, one useful thing that we can do is we can explore the situation where parallel lines are cut by a transversal, because then some predictable things happen, some useful things. Oops. Okay, so parallel lines and transversals. So we want to prove and use some results about parallel lines and transversals. So for example, this is the first really big thing that we talked about with parallel lines and transversals. This is the corresponding angles postulate. This is not proven, this is accepted. Makes sense though, doesn't it? If we have 2 parallel lines cut by a transversal, then doesn't it make sense that pairs of corresponding angles must be congruent? Okay? How could we sort of prove that to ourselves? Well, what would happen if these lines extended forever? Let's say they were really bright so we could see them from a great distance. as we walked further and further and further away from this, assuming these go forever, right? What would appear to happen to these two lines as you get further away? They'd appear to get closer together, wouldn't they? And at some point, as we got super far away, we wouldn't even be able to distinguish the two lines, and they would look like one line. Would anything happen to the size of this angle? It'd stay the same the whole time, wouldn't it? So can you see that that's kind of an informal proof in a way that that has to be true, right? The other way would be if I were to translate this line, and that's a word we haven't talked about this year yet, but you've probably used it in the past. What does translate mean in geometry? Say it again. To move something, to slide it, but we're not going to rotate it or anything like that. All we're going to do is just move it in its current position. So if I were to translate the bottom line, if I were to slide it upward, we would all agree that those two angles would overlap perfectly, right? And so therefore they must be congruent. Okay, so that one we'll just accept. There's some other things that you're going to prove and we're going to use from here on out. Here's one of them. These are all theorems because they are built from that postulate that we just talked about. They're built from the corresponding angles postulate. So the alternate interior angles theorem says, oh, and I want to go back real quick to one other thing. What's the hypothesis of this statement? Okay, so if we've got a situation where two parallel lines are cut by a transversal, then the conclusion is corresponding angles are congruent. Real quick, one other little thing I'll mention here. What's a way that we could visually demonstrate that those two lines, how could we mark this drawing? We'd say in geometry, how could we mark the drawing so that we show the lines are parallel? Remember, Elton, remember?
Put an arrow on both.
Yeah, you can do something like this. Okay, that's supposed to be an arrow, right? You get the idea? So if I have a single arrow on both, that means they're parallel. What does this mean?
Those two are parallel.
Okay, there's another set of different parallel lines. Okay? You've seen that before probably. Okay.
It's not parallel, it's just straight.
Yeah, okay, well, true. But it doesn't matter if they're straight or not, does it? In geometry, we don't care about how good the drawing is. We just care about the information stored on the drawing. Okay, so then we can do similar stuff. We can take the same hypothesis. If two parallel lines are cut by a transversal, then here's something else that's true. We know that pairs of alternate interior angles are also congruent. That's always true. You're going to prove that. By the same token, we know that same hypothesis, if two parallel lines are cut by a transversal, then we know that pairs of consecutive interior angles are supplementary, meaning what? Their measures add to 180, good. And we also know that pairs of alternate exterior angles are congruent, okay? So here's what I want you to do then. We're gonna quickly gather into some groups. I'm gonna put your groups up right now. It's gonna be totally random groups.